Hello, in today's video, I'll be solving questions on A2 Electrochemistry from February March 2019, paper 4-2. Question 4, C. I. Use standard electropotential data from the data booklet to calculate E naught of cell for the reaction 2Cu2 plus aqueous plus 4I minus aqueous giving 2Cui solid plus I2 aqueous. From the data booklet, every electropotential equation is written in the reduction form. So you know reduction is the gain of electrons. So you can see from Cu2 plus to Cu plus, and also from I2, which has an oxidation number of 0, to I minus with the oxidation state of -1. The electropotential value for the Cu2 plus to Cu plus equation is 0.15 volts. That of the I2 to I minus equation is 0.54 volts. The E naught of cell is gotten by adding the two half cells to form a complete cell. So the equation for the complete cell is given on top over here. Now you can see that for the Cu2 plus, it has been reduced to Cu plus in this case. So it means that the Cu2 plus to Cu plus equation has not been reversed. So it means the electropotential value will still remain 0.15 volts. Remember, we said every electropotential equation is written in the reduction form. But in the complete cell equation, the I minus equation has been written in the oxidation form. So which means that we have to reverse the sign of the electropotential for this equation. So that will be minus 0.54 volts. So the E naught of cell is giving us negative 0.39 volts. II. Explain how the value of E naught of cell calculated in I predicts that the reaction is not likely to occur. The E naught of cell calculated in I is negative, and anytime the E naught of cell is negative, the reaction is not feasible or the reaction is not likely to occur. Now we can prove this by calculating the Gibbs-free energy for this equation. Remember, the Gibbs-free energy is giving us negative NF E naught of cell. The N is the number of electrons transferred in the equation. The F is the Faraday's constant. And of course, the E naught of cell is what you have calculated in I above. The number of electrons transferred in this equation is 2, because to add these two half cells together, the number of electrons must be the same. So it means that we have to multiply this equation with 2. And so it means that if you check the two equations, you can see that the maximum number of electrons you can find by the two equations is 2. And so that means that our N is 2. So that will be negative 2 times the Faraday's constant is 96,500 times the E naught of cell that we calculated, which is negative 0.39 volts. Now, if you multiply these values together, you can see that we are getting a positive Gibbs-free energy value as 75270 joules. Now, anytime Gibbs-free energy is positive, the reaction is not feasible. So for a reaction to be feasible, Gibbs-free energy must be negative. And so this is also another way to also say it. But it is better to go for this, though every examiner understands this, that once the E naught of cell is negative, the reaction is not likely to occur. In an experiment, a solution of I minus aqueous is added to a solution of Cu2 plus aqueous. A reaction does not occur, and a precipitate of sparingly soluble Cui solid is formed. The concentration of Cu2 plus aqueous remaining in the solution is 1.00 times 00 mole per decimeter cube. The concentration of Cu plus aqueous in a saturated solution of Cui is 1.3 times 10 power minus 6 mole per decimeter cube. I. Use the next equation to calculate the electric potential E for the Cu2 plus / Cu plus half cell in this experiment. The next equation is used to calculate the electric potential of a non-standard half cell. So the electric potential of a non-standard half cell is E, is giving us the electric potential of the cell under standard condition plus 0.059 over Z log concentration of oxidized species divided by the concentration of reduced species. So in this equation, Cu2 plus E minus giving Cu plus, this is the oxidized species and this is the reduced species, because the oxidation state of this is +2, so oxidized. The oxidation state of this is +1, so it is the reduced form. The E is giving us 0.15, that is the E naught for this half cell, plus 0.059 divided by 1. The Z is the number of electrons transferred. And you can see that in this equation, it is only one electron. Log concentration of the oxidized species, which is 1, divided by the concentration of the reduced species, which is 1.3 times 10 power minus 6. So if you solve this, you should get 0.50 volts. IV. Copper 1 chloride is also sparingly soluble in water. Suggest why the following reaction does not occur. 2Cu2 plus aqueous plus 4Cl minus aqueous does not give 2CuCl solid plus Cl2 aqueous. To solve this, we need the electric potential values for the two half cells that came together in this equation. From the A-level data booklets, the electric potential equations are always written in the reduction form. So the value associated with this is 0.15 volts. That of the Cl2 and the Cl minus equation is 1.36 volts. Now we can see that to form this cell, the Cu2 plus to Cu plus equation has been maintained. So it means that you have to maintain the electric potential value at 0.15 volts. But that of the Cl equation has been reversed. So in the complete cell, we are rather seeing Cl minus to Cl2, which is a reversed equation of this. So it means that we also have to reverse the sign of the electric potential value when we are doing the calculation. So that will be minus 1.36 volts. And this gives us negative 1.21 volts. This value is very negative. And so remember, we said when the electrode potential value of the cell is negative, then it means that the reaction is not feasible or is not likely to occur. See you in my next tutorial, and do well to subscribe to this channel and hit on the notification bell.